So today we are going to start talking about writing equations of tangent lines. We've been talking a lot about what part of the tangent line? The slope, right? Because the slope of the tangent line is the same thing as what? The derivative, right? Derivative, slope, and instantaneous rate of change. Slope of the tangent line, instantaneous rate of change, right? I'm putting this at the top of everything because those all three are the same thing, right? So we've been talking a lot about the slope of the tangent line. Today we're going to write equations of our tangent lines, okay? There are two things you need to write the equation of a line. What's one of them? What's one thing you need to know to write an equation of a line? Slope, right? Well, that's good because the slope is the derivative, right? So we'll need the derivative to write the equation of a tangent line. What is the other thing you need to be able to write the equation of a line? It could be the y-intercept. It doesn't have to be the y-intercept. It could just be any what? Point. It could be any point. If it's the y-intercept, it's easy. Y equals mx plus b, right? But we don't usually have the y-intercept in this class. So we use the point slope form all the time when we write equations of our lines. Because for that, all you need is a point, right? It doesn't have to be the y-intercept, okay? So just a reminder of what point slope form is. It's y minus y1 is equal to m times x minus x1. So you put your point in for the x and the y1, and then you put your slope in there. And it's easier because you don't need the y-intercept. You don't have to find the y-intercept to write the equation of your line, okay? This is why you learned point slope form. It was all getting ready for calculus, okay? So let's go ahead and start an example here. So this is the graph of g of x right there. We've got a quadratic. You can tell it's a quadratic. We'll come back to the graph in a second. But the first thing we're going to do is find the derivative at -4. So when you're finding the derivative of a point, find the derivative first and then plug in the point. You cannot plug in the point and then take the derivative. If you plug in the point and take the derivative, you're going to get 0 every single time. And this class would be very boring if the answer was always 0, okay? So take the derivative and then plug in the point. So we need to find the derivative of this function, but right now we can't use the power rule because that's a composition of functions. Some of you know a shortcut. We're not there yet, so don't use the shortcut, okay? So we need to do what to be able to use the power rule on this, do you think? What can we do to that to get it to look like a nice polynomial? Yeah, expand it. So we're going to do 1/2 times x plus 2 times x plus 2 minus 4. You're not going to square the x. You're not going to square the 2, right? Because we know that's illegal math. You're going to multiply those together. So we'll get 1/2 times x squared plus 4x plus 4 minus 4. So that'll be 1/2 x squared plus 2x. 1/2 times 4 will be 2, minus 4 will be minus 2. Did we find the derivative yet? Can you find it now using your special rules that you're going to do on your quiz tomorrow? Go ahead and find the derivative now. This is now in the form where you can find the derivative, so go ahead and find it. All we did was expand. So go ahead and find the derivative now. Use your special rules. So 2 times 1/2 will be 1. Subtract 1 from the exponent and you get 1. The derivative of 2x will be 2, and the derivative of -2 is 0. So g prime of x is just x plus 2. All right? Now, they asked us to find g prime of -4. So what do we do to find g prime of -4? Plug in -4. So g prime of -4, what do we get if we plug -4 into that equation? -2. But what does this mean? What does this mean that g prime of -4 is 2? What is that on a graph? What is that? What is this number right here? The slope of the tangent line at what point? At -4. Okay? So if you were to draw the tangent line at -4, we just found that the slope of that line is -2. Now, you could have drawn it and approximated it, and you might have been able to get -2, right? But that would have been an approximation. This is the actual value of the slope of that line, okay? Now, in step 2, we're going to write the equation of this line at x equals -4. So what do we have? What important information did we just find? The slope. So we found the slope of the tangent line at x equals -4. And what was the slope of the tangent line at -4? -2. So that's half of what you need to be able to write the equation of your tangent line. We need a slope and we need a what? A point. It doesn't have to be the y-intercept. It can be any point on this line. Well, you already know the x value of your point. If we're finding a point on the tangent line at x equals -4, what's the x value of your point? -4, right? So you already have an x value. What's the y value at that point? Do we have a point on our tangent line here? Yeah, this guy right here. Isn't this guy right here on our tangent line? Isn't this point on our tangent line? Right? Because we're drawing the tangent line through this point, right? So what is the y-coordinate of that point? -2. So then our equation of our tangent line, we'll use our point slope form. Y minus the y value, so y minus -2 equals the slope, -2 times x minus the x value. And simplified, that would be y plus 2 is equal to -2 times x plus 4. This is the equation of the tangent line at x equals -4. So that's the equation of this blue line on the graph. Okay? This is not in y equals mx plus b form. Does that mean this is not a line? Is this still a line? Yeah, y is a function of x, right? There's just a 2 on this side, and this stuff has not been multiplied out. Could you turn that into y equals mx plus b if you wanted to? Sure. You could distribute the -2. You could subtract the 2 to the other side. But in calculus, most of the time, we just leave it like this. All right? We usually don't put it into y equals mx plus b. If they ask you to on a multiple choice, it's really easy, right? You could just put it in that form. But we start here because it's easy to find a point, right? It's not always easy to find the y-intercept, okay? So that's our tangent line. Now what we're going to do is we're going to plug -3.9 into this tangent line, okay? So I'm going to go ahead and move the 2 over to the other side here. So I will have y is equal to -2 times x plus 4. I'm not going to distribute. I'm just going to move the 2 over there. So the y is by itself. And we're going to find the value of y when x is -3.9. So let's plug in x equals -3.9. And we're going to practice some simple decimal math because you should be able to do this without a calculator. Okay? So let's practice some simple decimal math. -3.9 plus 4 will be 0.1, right? So I have -2 times 0.1 minus 2. And then what's 0.1 times -2 going to be? Just -0.2, right? You're multiplying by 0.10, right? So if you multiply 2 by 0.10, you'll get 0.2. So -0.2 minus 2 will be -2.2. So if I plug in x equals -3.9, my y value is -2.2. So what I just did here is I took my tangent line and I zoomed in really, really close, and I plugged negative 3.9 into my tangent line, and I got negative 2.2 out, which that kind of makes sense, right, about where we would be on our tangent line. So that's the point on our tangent line, okay? Now, if we plug in negative 3.9 into our function value, that's going to be on the black line, right? Those are not going to be the exact same point. The only place these are the exact same is at this point, right? So even just a little bit further away, the tangent line and the graph are going to be like this. Like, you can't really see it right now because I can't even zoom in that much. My lines are too thick, right? But as soon as we get away from negative 4, they're going to split, right? But is it going to be that big of a difference between those two? No. In fact, right now, it looks like they're on the same point if you were to put a point on both the graph and the tangent line at that point, right? So that value we just got, negative 2.2, that probably is very similar to the value of the function at negative 3.9, right? Because they're really, really close together. So now let's go ahead and plug negative 3.9 into the original function g. So that will be 1/2 times negative 3.9 plus 2 squared minus 4. Now this, I would expect you to use a calculator for. This is not going to be a very nice number. Can I just tell you what the calculator will give you? Is that okay if I just tell you that? Okay. So if you plug that into the calculator, you're going to get negative 2.195. So if this is negative 4, right, and our tangent line went like this, at negative 3.9, we have our function value and our tangent line value, and they're really close together, right? Are these the same number, though, when we plug negative 3.9 into our line and our function? Are they the same number? But are they really close? Yeah, right? So our tangent line can be used to approximate values on our function as long as we pick something really close to where we drew the tangent line. If I try to do it all the way out here at like negative 2, that's not going to be a good approximation, right? Because negative 2 on the function and negative 2 on my tangent line are going to be really far away, right? But really close to that negative 4, plugging in something nearby, those are going to be really close together, right? Because you can't even see it up there, how they're not that different. So these values are really close, especially if we don't have a calculator. This is really easy to do, right? This is really easy math, but this, not so easy, okay? So this is often what we're going to do with tangent lines, is use them to approximate function values. So they're really close together. So we can use tangent lines to approximate values of the function nearby. So they're really close together, so we can use tangent lines to approximate values of the function nearby, okay? So that's a common thing we're going to do with our tangent lines. Okay, so let's look at another example here. This is g of x here. On this graph, it says, does the graph of g have a horizontal tangent? Is there a place where g has a horizontal tangent? Where do you think it has a horizontal tangent? So the slope of the tangent line is 0. Yeah, at 1, right? Doesn't it look like we've got a horizontal tangent right here? Okay, so it looks like x equals 1. There's a relative max there. And we know what relative max is. The derivative will always be 0, right? When you hit that peak. But let's confirm this algebraically. So let's show that the slope of the tangent line is 0. How would you show me the slope of the tangent line is 0 using an equation? What would you do to the equation? find the derivative, right? The slope of the tangent line is the derivative, right? So we're going to find g prime of 1. And we're going to see if that's actually 0. Because if g prime of 1 is 0, then we are correct, right? That the derivative or the slope of the tangent line is 0 at 1. So let's start with this function g. Right now, it's not in a nice form for us to use the power rule. So let's rewrite that square root as x to the 1/2. And then we'll go ahead and take the derivative using our power rule. So bring down the 1/2. 1/2 times 2 is 1. Subtract 1, and you'll get negative 1/2. Derivative of negative x is negative 1. Derivative of 2 is 0. Do we like having negative exponents in our answer? No. So let's rewrite this as 1 over the square root of x minus 1. And then I'm going to make it one big fraction. So I'm going to multiply top and bottom here by square root of x so that we have 1 minus square root of x over square root of x. If you find at any point you want to use this version, if that's prettier, you can use that one. But there's going to be some points that we like this one better. So we'll leave this one here. So now let's find g prime of 1. Plug 1 into that equation. What do you get if you plug 1 into that equation? 1 minus the square root of 1 will be what? 0 over 1 is going to be 0. So where we write, is there a horizontal tangent at x equals 1? Is the slope of the tangent line the derivative 0 at 1? Yes, right? So we've seen this algebraically and graphically, okay? All right, where is this guy where is the derivative negative? Where's the derivative negative? So where's your slopes negative? Are our slopes going to be negative over here? On this side? Are they going to be negative over here? Yes, right? All of these guys are going to be negative slopes, right? If I draw slopes there. Is it decreasing over here? Yeah, right? So when it's decreasing, the slope better be negative, right? Because this is g of x, right? My function, it starts increasing up to the peak, and then it starts decreasing. So g prime will be less than 0 from 1 to infinity because g is decreasing. You could also see it in your equation. No matter what value I plug in from 0 to infinity, the bottom is going to be positive, right? If I plug in a positive number, I'm going to get a positive number out. But when will the top here be negative? When you plug in numbers bigger than what? 1, right? If you plug in 1/2, that'll be positive, right? But the second you get to 1, you're going to get 0. And then anything bigger than 1 is going to make that negative, right? And so the derivative will be negative. The slope of the tangent line will be negative from all the way out here. Plug in 4, 5, 6, 7, 8 into that, and your derivative will be negative, right? So when is our derivative positive? Well, anything between 0 and 1, right? Plug in anything between 0 and 1, that guy will be positive. Our function is increasing. Our slopes are positive, right? So anything from 0 to 1, it's going to be increasing. You could say for a reason because g is increasing. But we can also see it in the equation. Now the next question asks us, for what values is the slope of the tangent line equal to 2? That's going to be really hard to do exactly on the graph, to figure out exactly where the slope is 2, right? You could try to approximate, but that's going to be hard to do exactly on the graph. So we're going to have to do this algebraically. Well, what is the slope of the tangent line? The same thing as the what? The what? The derivative. So we want to know where the derivative is what? Equal to 2. So take our derivative equation. I actually, for this part, I like this version better. So let's start with this version before we combined it into a fraction. Can you solve that to figure out where that equals 2? Can we solve where the derivative equals 2? What can we do first? Move the 1 over, and we get 1 over the square root of x is equal to 3. We could multiply by the square root of x here. Then what would you do to solve for x next? Divide by 3. Square both sides. And you get x equals 1/9. That would be very hard to find on the graph, right? That the slope is 2 at 1/9. That would be very hard to approximate on the graph. So you just use the algebra to show that the slope of the tangent line was 2, because you showed that the derivative was 2. And the derivative is the slope of the tangent line. All right, let's do another equation of a tangent line problem. So we're going to find the equation of the tangent line at x equals 4. So what two things do we need to write the equation of a tangent line? Or any line for that matter. What two things do we need? A point and the slope, right? So we need the slope of the tangent line at x equals 4, and we need a point on the tangent line at x equals 4. How are you going to find the slope of the tangent line at x equals 4? Exactly. Not approximately. The slope of the tangent line is the same thing as what? The derivative. So what are you going to do with your derivative? You have a derivative right here, right? Either one of these versions is the derivative. What are you going to do with that to find the slope of the tangent line at 4? Plug in 4, right? The derivative at 4, that is the slope of the tangent line. I'm making you repeat this like 80 million times for a reason, right? The derivative and the slope of the tangent line are the same thing. So the derivative at 4, whichever version you want to use, square root of 4 minus 1, 1/2 minus 1 will be negative 1/2. We know the x value of our point is 4. On this one, you could find the y value pretty easily. If we do our tangent line at 4, what's going to be the y value there? At that point? 2. But a lot of times you're not going to have a graph, right? You're just going to have an equation. So what if I didn't have that graph? How would I figure out that the y value at that point is 2? Well, this point is on your tangent line, but it's also on your function, right? It's on both, right? Because you're drawing the tangent line there. So if you need the y value and you know the x value, just plug 4 into your function, right? So we could plug 4 into g. And we would get 2 times 2 minus 4 plus 2. Which is 2. So our point is at 4, 2. So on this one, you could see that on the graph, for sure, right? But most of the time, you're not going to have a graph. You're just going to have an equation. So you're going to need to plug that value into the equation. That point is both on your function and your tangent line, because you're drawing the tangent line to the function at that point, okay? So you can use the function to do that. So now our equation will be y minus 2 is equal to negative 1/2 times x minus 4. So that is our equation. I already drew the line up there. That's the black line, okay? And so then it says, use this equation to approximate g of 4.1. So if I want to approximate g of 4.1, if I plug that into my tangent line equation, that will give me a good approximation. So I'll go ahead and add the 2 over here. So we'll have negative 1/2 times x minus 4 plus 2. That way y is by itself. And then we'll take that tangent line, plug in our x value. We'll get negative 0.5 times 0.1 plus 2. That'll be negative 0.05 plus 2, or 1.95. All right, so on these problems here, it gives us a table of values for h prime. Okay, so this is not about h, this is about h prime here. So we know a bunch of values, and this is the important part here. The zeros on this table are the only zeros. So we know that the derivative is 0 at negative 2 and 7 and nowhere else. So for example, if the derivative changes from 11 to 5, we know it can't go like between negative and 8 and negative 5. We know the derivative can't go from like 11 to negative 7 to back to 5. It can't go to like negative 7 because it would have to go through 0 again. So we know it's going to stay positive everywhere in between these values here up until negative 2. And that's even beyond negative 8, so beyond there. And so it's going to stay negative between 7 and 12 and everything beyond 7 and 12 because the derivative is negative during these values. Okay? So when we want to see when the function is increasing, when h is increasing, we're going to be looking for where h prime of x is greater than 0. And so that's going to be from h is increasing from negative infinity to negative 2, because it's going to be positive all the way from negative infinity up until negative 2 here at this x value, because that's when the derivative is 0, because it's positive and it'll be positive forever to the left. And then if h is decreasing, we're going to be looking for where h prime is less than 0. So h is decreasing when the derivative is negative. So it's negative here, so that'll be from negative 2 all the way to 7. And then it's also negative here, so that'll be from 7 all the way to infinity. So h prime is positive on negative 2 to 7 and 7 to infinity. So h is decreasing on negative 2 to infinity all the way through 7. And it says give reasons for your answers. Well, these are reasons right here. This is your justification. Okay? So at what values does h have a relative maximum? So if we're looking for a relative maximum, we're looking for where the function goes from increasing to decreasing. So we're going to be looking from where h prime changes from positive to negative. Well, that happens right here at x equals negative 2. Because the derivative starts positive and then goes to negative at that point. And that's your justification. So if you write down what you're looking for first, you will justify your answer. So when does it have a relative minimum? We're going to be looking for where h prime, when we go from decreasing to increasing. So h prime changes from negative to positive. Well, at this 0, we go from negative to negative, and there's no other zeros. So there's no place where it changes from negative to positive. So there are no relative minimums. because this happens nowhere. And again, this is your justification. So if we want to write the equation of a tangent line at x equals 3, we need the slope of the tangent line at x equals 3, and we need a point on the tangent line at x equals 3. Well, the point, we already know the x value is 3, and they tell us that the function is 2 at 3. Well, remember, our tangent line that we're going to be drawing, wherever h looks like, we don't know what h looks like, but wherever it looks like at 3, we're drawing the tangent line at that point, right? So this point right here is going to be on your tangent line and on your function. So they tell us right now that when you plug in 3, the y value is 2 on h. So that's also going to be the point on your tangent line, 3, 2. And then we already know the slope of our tangent line as well, because if you look at your table, they give us the derivative at 3. So h prime of 3 is equal to negative 3. So that's the slope of the tangent line. So then to write the equation of your tangent line, it just be y minus 2 is equal to negative 3 times x minus 3. Now we'll use that tangent line to approximate h of 3.1. So we'll go ahead and move that 2 over. So we'll have negative 3 times 3.1 minus 3 plus 2. I just moved the 2 over to the other side, plugged in 3.1 for x. And we'll have negative 3 times 0.1 plus 2. So that'll be negative 0.3 plus 2, which will be 1.7. You should be able to do that math by hand. So that's an approximation of the function value at 3.1 by plugging it into the tangent line, because those two values will be really close together at 3.1. Now it's asking us about some limits. Well, we already talked about up here how the derivative will be negative all the way till negative infinity. So if that means it's decreasing, right? Increasing from negative infinity to negative 2, right? We know that it's increasing from negative infinity to negative 2, and then it starts decreasing again until 7, and then it's decreasing again and again and again. We kind of know that that's what our function h is going to look like, right? Because we know it starts increasing from negative infinity to negative 2, then it starts decreasing after negative 2 until we get to 7, and then it goes to 0, then it starts decreasing again, right? So we know that the behavior as we go to negative infinity, it's going to go to negative infinity. The function goes down here forever, and then over here the function also goes down forever. This one is interesting because they give us the derivative, and they want the instantaneous rate of change of f at x equals 4. Well, that's just the derivative at 4, and they gave us the equation. So we don't need to find any derivatives. We just need to plug 4 into that. And we'll get negative 56. Then they ask us for the equation of the tangent line at x equals 4. So we need the slope of the tangent line at x equals 4. Well, that's going to be the derivative of f at x equals 4. Conveniently, we just found that in the previous question. So that's negative 56. And then we need a point on the tangent line at x equals 4. Well, the x value is 4. We don't want to plug 4 into this equation to get the y value because that's the derivative. We want to plug 4 into the original function. Well, what's nice is they did that for us. So this is your point on your tangent line, because remember, f is somewhere, and at 4, that tangent line we're drawing is going through this point. So if this is f, right, and that is going to be for negative 1 because of this right here, then that point will also be on your tangent line. So then you can write the equation of your tangent line, y plus 1 equals negative 56, x minus 4.